here's a conservation of energy problem with a variety of things that could be asked here. And it looks like this. Initially, there's a mass here at the top of an incline. It's a distance h naught above the ground. And what we see at other points in the problem here is that there's a frictional patch right here. So a patch where it gets rough here for about a distance delta d, something like that. Okay? And there's a spring over here. It's frictionless under the spring. Could be friction under here, but for now it's frictionless. There's a spring constant K in there. So what the problem would like to know then is given this scenario here, how far will the mass compress the spring? That's sort of a given in there. And so what I see here then is I do see this work due to friction going on. So I'll start with my traditional equations here. E initial is equal to E final plus the work due to friction. Now I'll put the work due to friction over there because what I envision happening in this problem here is that when this block here goes all the way down, runs over the friction here and encounters the spring here, it'll be against the spring here, but of course the spring will be all bunched up now. The spring will get itself compressed here by a distance delta S. And so I'll see this block here sitting against the spring here stopped. But because the block must have gone over this rough patch of friction before it went up against the spring and it got stopped right there, this whole surface here is going to be nice and warm. So I'll draw it in red there because it's going to be barbecued. And that's the work due to friction that we need to account for. As the block slides over the surface, there's net energy mechanical energy flux out of the box into the surface here. The surface is going to be warm. So if I just fill in this equation here, let's just do that and see what we get, and then we'll discuss it and wrap up here. The initial energy of the system here I see is an mg times h naught. There's that block at distance h naught above the ground. The final mechanical energy that I see over here is going to be the compressed spring, the 1/2 k times delta s squared. The block certainly isn't moving when it reaches the spring here, so it doesn't have any kinetic energy in the final sense over here. It's down at ground level, y is equal to 0, so it doesn't have any potential energy either, so there's none of that. So I just see a compressed spring, 1/2 k delta s squared, because again, the block is sitting here all bunched up against a compressed spring now. What about the work due to friction? Well, of course, this is going to be plus the frictional force times delta d, where delta d is that distance over the barbecue surface that it slid. And I know that the frictional force is equal to mu times the normal force. And I know that the normal force is mu times mg. Excuse me, the normal force is just mg. The normal force for a block on a flat surface is just m times g. So if I fill all this stuff back into my main conservation of energy equation, I get mg times h naught is equal to 1/2 k times delta s squared plus mu times mg, there's friction force, times delta d. So I can sort of tie all this together and say, hey, there's my core conservation of energy equation here that involves this term here, which is the work done by friction. And this is what goes into making that surface nice and red and warm when the block slides over like that. So depending on what your problem is asking, you can start connecting some things now. They might want to know what h naught would have to be to achieve some compression here, or how long does delta d have to be for some compression to be achieved given some h naught or whatnot. But this will be your core expression right here, and you can sort of definitely adapt it to whatever the problem might include. But try to remember the core, where this is coming from right here. The initial mechanical energy is equal to the final mechanical energy plus the hot surface of the work that friction must have done.